In this video, we are first going to finish up our discussion of injective and surjective functions that are given by formulas. And then we're going to introduce two different concepts, one being the images of subsets of the domain, and the other being inverse images of elements of the codomain. So first we're going to do an example of a function given by a formula and showing that it is injective and surjective. We're going to define what it means to be the image of a subset of the domain of a function. And then we're going to define the inverse image of an element of the codomain of a function. And then finally, we're going to show an example of finding an image and inverse image in an example function. All right, so to talk, before we get into the example of injective and surjective functions, I want to introduce a new model of functions that is actually going to be very helpful to us when we're solving these problems. And that is called the thrower-catcher model. So in this model, in our old model, our function was either a machine or a piece of code that did something. Now our function is going to be a coach who has a group of players who are, some of them are throwers, and some of them are catchers. So what happens is each thrower has one ball that they have to throw, and the coach instructs each thrower, who is the input of the function, which catcher, and in other words mean the output, they throw the ball to. So every thrower throws the ball to the catcher. The function, who is the coach, tells the throwers who to throw the ball to. So as you may have figured out already, the set of throwers collectively are the domain of our function. The set of catchers are the codomain. And I should note that it is possible that not all catchers have thrown a ball, just as in any other codomain. It is also possible that you have a catcher who has thrown more than one ball. So good luck for them catching all those balls. So here is what injective and surjective functions look like in the thrower-catcher model. So for injective functions, it means that no catcher gets thrown more than one ball. If you did have a catcher get thrown more than one ball, that would mean you'd have an output that is associated with two different inputs. And injective means that never happens. Surjective means that every catcher gets thrown at least one ball, right? So remember, the catchers are the elements of the codomain, and that means that everybody in the codomain is actually an output. They get thrown a ball. So let's see if we can apply this to the function. This is from the integers to the integers. So the domain and codomain are both the set of integers. F of x equals x plus 2. Just a nice little simple function to give us the idea of how the mechanics of these types of arguments work. So let's go ahead and see if we can show that f is injective, surjective, both, neither. We'll see. So for injective, let's see if we can imagine what would have to happen if f were not injective. So let's see if we can look at the counterfactual, right? There would have to be two throwers, and those are inputs that would be throwing the ball to the same catcher, which would be the output. So let x1 and x2 be these hypothetical throwers, and for the sake of this argument, we're kind of pretending that they're different and seeing what would have to happen. And so then y is the catcher that they're both throwing the ball to. So what does that mean? Well, if x1 is the thrower, y is the catcher, that means f of x1, which is the output, is equal to y, which is the output, which is the catcher in this case. Same with x2. x2 is the input, y is the output, that means f of x2 is equal to y. And notice in both of those equations, both f of x1 and f of x2 are equal to the same thing, y. That means they're equal to each other. So f of x1 equals f of x2. Now we have a nice formula for f, right? F of x equals x plus 2. That says whatever your input is, you add 2 to it to get your output. So if your input is x1, you add 2 to that to get your output, x1 plus 2. If your input is x2, then your output is 2 more than that, x2 plus 2. Now we've already noted that f of x1 and f of x2 are equal. That means x1 plus x2 is equal to x2 plus 2. And now we can play with this equation, probably subtracting 2 from each side seems a reasonable thing to do, and we get x1 is equal to x2. And let's see what we've said here. We were imagining that x1 and x2 were two different throwers that threw to the same catcher, and what we ended up with is that x1 and x2 were actually the same thrower. So that tells us that the only way to have two inputs with the same output is if the inputs were the same all along. And that tells us that F has to be injective, that it can't have two different outputs giving you the same input, or two different inputs giving you the same output. All right, so now let's look at the issue of being surjective. So the question is, does every element in the codomain, by which I mean every integer, get thrown a ball? So is every possible catcher, do they get thrown a ball? Well, let y be some random element in the codomain. It could be any element, right? And what we're saying really, in reality, y, it could be any integer. So the question is, how can we tell whether y catches anything? Well, the most straightforward strategy for this is to actually try to find out who, if anybody, throws the ball to y. Is there any integer in the domain that actually throws the ball to y? And if so, which one? So let's see if we can figure out which one it is by saying, well, let's pretend there's a thrower x. Let's see if we can figure out what x is. Well, if x is the thrower who throws the ball to y, that means that f of x equals y. That's exactly what it means for x to be the thrower, y to be the catcher. So we know f of x equals x plus 2. X is the input, right? So that means y is equal to x plus 2. And so if we solve for x, because remember, we want to solve for x because we want to find out who throws the ball to y. X is the one who presumably throws the ball to y. Let's see if we can figure that out. That's pretty easy to do in this case. X is equal to y minus 2. And now the question is that x equal y minus 2 a legitimate thrower who throws the ball to y? Right? Well, if there is a thrower, that has to be it. That's what we've shown. If there is a thrower that can do it, it's got to be y minus 2. Let's see if y minus 2 is actually a legitimate thrower. Is it and first of all, is it an input? Is the function actually going to accept y minus 2 as an input? Well, remember, the function only accepts integers. So in order to accept y minus 2 as an input, it has to be an integer. So the question now is y minus 2 an integer? Well, we know y is an integer because it was in the codomain, which was a set of integers. And if I take y, an integer, and subtract 2 from it, it's going to be a different integer, but it's still going to be an integer, which means it's acceptable as an input for our function. Right? So it's in the domain. So now let's see what happens when I actually put it into the function. Do I get y? That's what I'm looking for. Well, remember what the function does. It takes your input and adds 2. So it takes your input, which is y minus 2, adds 2 to it. Notice that negative 2 and the positive 2 cancel each other out, and that gives us y. So not only is y minus 2 in the domain, but its output is y, which is exactly what we were looking for. Remember, y could be any integer, which means and it's an output. So that means every element of the codomain is an output, which says that f is surjective. Okay, so now we're going to move on to a couple of new concepts called the image and inverse image of a function. And in order to understand those, well, I'm going to introduce yet a third model for functions. Okay, so this one's a little bit more tricky, so try to pay close attention to this one. So in this one, a function is someone who takes photos. So a photographer, right? So I got to tell you so I told you who the function is. I got to tell you who the inputs are, who the outputs are. The inputs to our function are the objects that a person takes photos of. So a person takes photos of some objects that are in the pictures. And then the outputs are the photos themselves. So inputs are objects, outputs are photos that are taking the objects, that you're taking the picture of those objects. And to be a function, right, to this photography to be a function, each object must be in precisely one photo. And you can kind of see why that is. If you had an object in two different photos, that would be an input that had two different outputs. So I should note that the object can be in a photo with other objects, right? So you can have a photo with more than one object in it, but the object itself can't be in more than one photo. All right, so that leads us to the following definition. Let f from domain A to codomain B be a function. If we have a subset of the domain, we'll call it S, the image of S is the set of all outputs, and remember, outputs are photos that come from elements of S objects, which are the objects. So if you look at all the possible outputs that you get from S, that's the image of S. So if you have another set T contained in the codomain, then we say the inverse image of T is the set of all inputs, by which we mean objects, that give us the outputs that are in T, photos. So if you look at all the inputs that can give you an output in T, that's the inverse image of T. So for our notation, our image of a set S is written f of S, and our inverse image of T is written f inverse of T. And I should note that f inverse of T is a notation we use even if f itself does not have an inverse function. So just want to make a note of that. All right, so I want to talk about the image and pre-image in terms of our photos, because that's kind of the name image sort of is reminiscent of what we were talking about in the photographer model. So what the image of S is, it says that is going to be all the photos that include at least one object from S. So S, you have a collection of objects, and what you're doing is you're looking for photos that have one of those objects in it. Maybe more than one, but at least one. The inverse image, well now, remember T itself is a collection of photos, and now what you're doing is you're looking for all the objects that are in at least one of the photos. So you're looking through the photos, you're making a list of all the objects in those photos. That combined list is going to give you the inverse image. So let's see if we can apply this to an actual function. So our function f is going to have inputs 1, 2, 3, 4, 5, and 6, and the outputs are going to be natural numbers, and I am going to express this function as an array. So the top row is the inputs, the bottom row is the outputs. And first of all, we're going to look for an image. So I'm going to look for the image of the set 1, 3, 4. So remember, 1, 3, 4 are the objects. We want to look at the photos. Remember, the photos are the elements on the bottom row. So 2, 5, 2, 7, 2, 8, those are the photos. So we want to look at the outputs that we get from 1, 3, and 4. Well, f of 1 is equal to 2. So 1 is the object, 2 is the photo. So 2 is one of the things in the image. F of 3 is also 2. That's already in there, so that doesn't add anything to our list of things in the image, but it's something that we have to consider. And then F of 4 is equal to 7. So if the only two photos that we get are 2 and 7, right? The only two items we get for our outputs. And that means the image of 1, 3, 4 is the set containing 2 and 7. Now, if we want to find an inverse image, I'm just going to find the inverse image of a single element 2. That means 2 is the photo, and we want to find out what are all the objects in that photo, right? So 1 is an object in the photo 2, if you think of 2 as the photo, right? So 1 is one of the objects because f of 1 is equal to 2. 3 is also one of the objects in the photo 2 because f of 3 is equal to 2. And also f of 5 is equal to 2. So we have 3 different objects in that photo. Those are going to be make up the inverse image, which means our f inverse image, f inverse of 2, is equal to the set containing 1, 3, and 5. So I do want to point out that the images and inverse images are sets, so make sure you write them as sets and not as individual elements of the domain and codomain. All right, so now I think you're ready to work on the activities in the PDF file called Injective, Surjective, and Inverse Images.